Quantum tunneling is a quantum mechanical phenomena where a particle is able to penetrate a barrier which has energy as in potential greater than the energy in motion of a particle, also known as kinetic energy. In classical mechanics, if an object does have enough kinetic energy to be more than the barrier, it would be able to pass through the barrier. But in quantum mechanics, if the object as in particle has not got enough kinetic energy, can still pass through the barrier, which is tunneling through the quantum system, though the energy tunneled through would be less than the energy before tunneling. What is interesting is the speed at which a particle goes through quantum tunneling. In the past experiments, particles tunnel the barrier faster than the speed of light, which got some attention from various scientists. Quantum particles, like the electron and proton, carry a property called particle-wave duality. So, an electron or proton would behave either as a wave or particle in nature. Quantum tunneling uses the subatomic particle's wave nature as a wave packet, as in wave function. If the wave packet hits the energy barrier, part of it would be reflected, but some portion penetrates the barrier, and there is probability of finding the reduced wave packet appearing on the other side. In 1962, Thomas Hartmann, a semiconductor engineer, found out that barriers act as a shortcut through time. What he found is that when a particle tunnels through, the time it takes to reach the other side is less than the time it took, even if the barrier wasn't there. This was astonishing, and even more was the case if we increased the thickness of the barrier. It would hardly increase in time it took to tunnel through. So basically, particles could hop from one side to the other side, traveling faster than light through an empty space. To see if this was true, two scientists suggest using the tunneling particle as a clock to find out if there is truly a difference in time. By using two particles, one quantum tunneling and not the other, and using a laser pulse, we can estimate the time difference. Using the second particle as a reference and the first together would go through a laser pulse, which is how initially the clock is synchronized. Since the first tunnels through, there would be a shift in rhythm of the wave, which would be the first laser pulse to cause interference with the second laser pulse. We can estimate time differences using this interference. If this phenomenon were true, the time difference would be positive and less time would be elapsed for the particle quantum tunneling. As of now, this experiment is in discussion. It is practically possible to be experimented with today's technology advancements. I will let you know if there are any updates.